So I want you to know about spectral normalization. I want you to know about progressive growing of your neural networks. And then we can continue to large-scale GAN training. Now we are getting better and better at generating high-quality images. The video is online. The paper is engineering. There is going to be a lot of techniques going on. And in the end of the day, you have a single objective: generate higher and higher quality images and make your customers happy. In the end of the day, have this in mind. You have some gamers, perhaps playing a game, and what you're doing is you have a product, and your product is going to do this. You're going to transfer low quality images on their computers, use their GPUs, which is usually a gaming GPU, and then increase the resolution of those images. And usually what you're going to do is you're going to use a GAN to do that. It's going to be conditional GAN, but you're going to be using a GAN framework. And usually gamers are really unhappy or really hard to satisfy or picky customers. They're going to immediately go online, put a negative review about your product, and then your company is going to suffer the consequences. And that's why you need to have a product that's actually capable of generating high quality images. And that's the idea here. You have some engineers in your company trying to increase the quality of the generated images. It's not enough to prove the concept. You want to productionize. Let's see, what are the big contributions? It is BigGAN. You have larger models, larger batches of your data. And larger batches is perhaps helping you escape the mode collapse. We are going to introduce self-attention GAN, so don't worry about it. We are going to be using hinge loss, we just saw it in the previous paper. You are going to provide your generator with some class, so you're just conditioning. For instance, if you're doing ImageNet, you're going to be generating all of the dogs. Condition on your class being a dog. You're going to be generating all of the cats, all of the fish, all of the airplanes, so far. But the way that you're going to be conditioning is you're going to change your batch normalization technique. In your batch normalization, you still compute the mean and the standard deviation of each layer over your mini batch. You still do that. You still subtract the mean, divide by the standard deviation. Now your layer is normalized. But then you have two learnable constants or two learnable vectors. One of them was the scaling, which is going to correct the scale that you just removed. The other one is going to add a bias. Those two parameters, they are going to be class conditional. So each class is going to have its own mean and its own variance or a scaling parameter. Is this point clear? The way that you do your conditioning. Okay, perfect. When it comes to your discriminator, you do conditioning the regular way. You just say, I have one hot vectors for my classes. Perhaps the class corresponding to dog is going to give you a vector that is 1 at the first location and 0 everywhere else. The one that corresponds to cat is 0 at the first location, 1 at the second location, and 0 everywhere else. And then you multiply by a matrix. The same way that you were doing and operating things when it came to language, it's the same scenario. These are your embedding matrices. You're going to be doing spectral normalization. And by the way, those embedding vectors are now going to be inputs to your discriminator. You're going to be doing spectral normalization, not only on your discriminator, on the generator as well. For evaluation, you're going to keep a moving average of your generator weights. And we saw this technique also before when we were talking about improved techniques for GANs. The other one is orthogonal initialization. You initialize your weights so that they are orthogonal. This other trick is truncation trick. What you do with generators is you generate a random vector from normal distribution, and then you push it through your architecture. This is going to generate a variety of images, hopefully. At the same time, you want it to be high quality. So there is this trade-off between high quality images and having a variety of images. And then you can balance that trade-off by truncating this normal distribution. Because normal distribution can go from negative infinity to positive infinity, you can control it. And this way, if you control the truncation magnitude, this is perhaps the entire normal distribution. You see a variety of dogs at different scales, but then as you decrease that threshold and you truncate more severely, you're going to have higher quality images, but then they are less various. You have the least variety. This one has a low quality, but it's actually different. It's a different image. This works if you do orthogonal regularization. Not only you initialize your weights in an orthogonal fashion, you're gonna try to maintain that orthogonality throughout your training. You're just gonna sum up some additional terms to your objective function. The other thing is, it's a good idea to monitor your singular values, the singular values of the weights in your matrices. Let it be the generator or the discriminator. And then if you see a pattern like this, where at some point your singular values are gonna explode, then it's a sign of mode collapse. Any questions about BigGAN? Was everything clear? So I go into a lot more details in those videos. So it's an assignment for you to watch them